6, Lesson 2, Operations with Radical Expressions. After this, you will be able to add, subtract, multiply, and divide radical expressions. Crazy as that might seem, that's our lesson. Okay, multiplying and dividing radical expressions. The objective here is to simply multiply them. Multiplying radical expressions means that you will be putting the things underneath the radical together, and the index stays on the outside. Sorry, I got a little distracted. Puppy was wanting some attention there. Okay, so when you take and you've got square root of 2 times the square root of 8, neither one of those are actually perfect square roots. So what we can do is we can take and multiply them so that we get the square root of 2 times 8, which is the square root of 16, which we know is 4. Now, the cube root of 5 is not a perfect cube. Negative 25 is not a perfect cube. So I can combine them underneath one radical. 5 times negative 25 will give me the cube root of negative, not negative 75, silly me. The cube root of negative 125, and the cube root here is negative 5. Okay? Now, we've got 3 here at the bottom that you can try. These are really pretty basic and pretty simple. Remember that you can do a negative root when you have an odd index. You've also already learned about the square root of a negative number, and that's I. The 4th and the 6th and the 8th root of a negative number does not exist. Okay, pause the video and try these. Hooray, you're back. Let's see how you did. 3 times 12, well, that's 6, because 3 times 12 means that you've got the square root of 36. What about over here? Let's move over. We've got the cube root of 9 times the cube root of negative 3 is, ooh, did you get that one? This became the cube root of negative 27. Well, how about the 4th root of 4 times the 4th root of negative 4? Bump, bada, bump, bump, bump. Oh, and that's not a 0. That's a null solution. This became the 4th root of negative 16. There's no 4th root of negative 16. There's a square root of negative 16, but not a 4th root. Okay? Now notice that when you combine these, you don't do anything to the index. You're just multiplying the items underneath the radicals. Right? Simplifying radical expressions means simplest radical form, that there's nothing left under the radical that is a perfect whatever root. So, square root of 7x cubed. I can also, just like you can multiply it together, I can break it apart and say I've got the square root of 7, square root of x squared, square root of x. Now remember, even index, yes. Even inside, no. So I don't have to worry about absolute values. Now, the x squared does come out, but then I still have the square root of 7x underneath. Over here, the cube root. Well, for this one, I've got the cube root of 8 times the cube root of 10. 8 times 10 is 80. The cube root of n cubed and the cube root of n squared, because n cubed times n squared is n to the 5th. So I just broke it apart. Now I know that I have 2 cube root of 10, and then I've got an n cube root of n squared. And I don't have to worry about absolute values because I have an odd index. Now, I'm going to put this all together, so I have 2n cube root of 10n squared. Not bad. You try the next two. And I know you can kind of see it. I know on this particular screen it shows up, but go ahead and try these. Pause the video. How did you do on this one? Why are there no absolute values? Even index, even inside, even out. This is E-I-E-I-E. Not E-I-E-I-O. Over here, I have an odd index. So when you simplify the radical, you don't have to worry about absolute values. And over here, by the way, if you weren't sure, you've got the square root of 25x squared, square root of 2, just breaking it apart. Here, you're going to have the cube root. The only thing that you can break apart here is x cubed, and then you still have 18x. Okay? Right. Moving on, multiplying expressions. When multiplying expressions, you can either simplify it before you multiply or multiply. It's really up to you. There are times where I would simplify things. For instance, here, 54x squared y cubed. Well, I know that 54 is the same thing as 27 times 2. And then I have my x squared, my y cubed. And by the way, no absolute values because I've got an odd index. Over here, I've got the square root of 5x cubed. And then I'm going to make this y cubed y. Why? Just because this way it's broken up into perfect cubes. Now, the cube root of 27 is 3. I'm going to leave my little cube root over here. So I took care of him. The 2 stays inside. The x squared stays inside. And then the y cubed, I can get a y out. The 5 stays inside. The x cubed, I can get an x out. The y cubed, I can get another y out, and then that y stays inside. Now I've taken care of each piece one at a time, so I have 3x, y squared outside, and then I have the cube root of 10x squared y on the inside. That's all I did. So you can simplify it, or I could have multiplied 54 times 5 and figured out that I have a cube root of 3 hidden somewhere in there. I find sometimes it's easier to take care of it when it's smaller, if possible. Okay, try these. You're back? Did you get this answer? Now notice we've got an even index. X, don't worry about. Y, I have to worry about. Even, and if it comes out and it's odd, I have to put an absolute value on it. Now first things first, 3 times 2 is 6. Then I have a square root of 7 x squared x, 3 times 7 x squared x, y squared. Well, the 7's come out, so I have 6 times 7. Then I can get an x and an x. I've got x squared. Then I've got a y squared, so I've got the y. Now I've got the square root, x squared, x squared. Now I have another x and an x. Ooh, so that x is going to come out. And then I'm left with 3 underneath. The y is in fact an odd, so it gets the absolute values. And I'm going to combine the x squared and the x to give me my x cubed. Okay? Good job. Now, dividing radicals. Same basic idea. When you divide radicals, you can combine the radicals or separate the radicals, whichever works best. In this case over here, I can do the cube root of 32 divided by -4. That's the cube root of -8, which is -2. So you can combine things very easily. Over here, we've got the cube root of 162 x to the 5th divided by 3x squared. 3 will go into, oops, I forgot my cubed root there. 54 times x to the 5th divided by x squared is x cubed. Now I have to simplify this because 54 is not a perfect cube. So I've got the cube root of 27x cubed and the cube root of 2. 27 times 2 is 54, which gives me 3x cube root of 2. Bada bing, bada boom. Okay, try these at the bottom. Did you pause the video and you're back? Woof. How'd you do on this one? Did you get 3? 27. Okay. Everybody good there? All right. Obviously, you can combine the 243 divided by 27. Hang on. It's acting a little bit weird. Hang on. There. Okay. 243 divided by 27 is 9. The square root of 9 is 3. Over here, did you get 2x square root of x? And there's no absolute value. Why is there no absolute value? Because we've got an even index even inside up top, but on the bottom it's an odd on the inside. Next up, we've got 1024 x to the 15th. We got odds inside, so we don't have to worry about anything. Whoops. See if I can get this so that we can look at it. 4x cubed, 4th root of x squared. Everybody good there? Great. All right, now continuing on, dividing radical expressions. Sometimes we have to rationalize the denominator. Because remember, the denominator cannot have a radical. So how do we do that? Well, we multiply the numerator and the denominator by a form of 1. So the square root of 3 divided by the square root of 3 is equal to the square root of 6 over the square root of 9, which leaves me with the square root of 6. Oops, sorry. Got a little crazy there with my writing. The square root of 6 over 3. Got it? Try the next one. See how you did. Okay, so here, did you notice that you can do the square root, make this a whole square root of x cubed over 5xy is then the square root of x squared over 5y. This then gives you x, because, well, it is a perfect square, over the square root of 5y. Now we can't have the square root of 5y in the denominator, so we simply multiply by the square root of 5y, square root of 5y. We have x square root 5y over 5y. Now, over here to the right gets a little bit trickier because it's a cube root. So now we have the cube root of 2 over 3x. But we can't just multiply by 3x, because if we did, let's try that. 3x over 3x. That now gives me the cube root of 6x over 9x squared. Huh, that hasn't fixed anything. If I do another 3x over 3x, I now get 3 over 18x squared over 27x cubed. That I can do, and I now get the cube root of 18x squared over 3x. See? You couldn't just multiply by the 3x. You need the denominator to be a perfect cube, not a perfect square. So think about that when you go to try these. Okay, across the bottom here, if you've tried them, great. If you haven't, pause the video and try them now. And I know you can kind of see the answers, but try them. It's important to practice. You're back? All right. Boom. I don't know why this is not. All right, so on this one, did you multiply by the square root of 5 over the square root of 5 and get the square root of 35 over 5? Nice. Now this one, notice I've got 10xy. And I've got the 2x cubed. Well, the 10 and the 2, I can get rid of the 2, and this will just make this 5. The x can go away, and this becomes x squared. So now I can take the square root of the x, and I have an x in the numerator. And then in the denominator, I have the square root of 5y. So I multiply by the square root of 5y over 5y, and lo and behold, your final answer is x root 5y over 5y. This one, hopefully you notice it's the exact same thing as this, because I can break this down into the cube root. 4, or 2 will go into 4 2 times. It will go into 6 3 times. And then notice we're right back to here. So I would actually want to multiply this by 9x squared over 9x squared, so that my final answer will be the same as this up here. All right? Okay. Next up, like radicals are radical expressions that have the same index and the same radicand. In order to add or subtract radicals, the radicals must be like. So 5 cube root of x minus 3 cube root of x. I can combine these. I have 5 of these things and I take away 3. That leaves me with 2 cube roots of x. Notice when I'm adding and subtracting, I don't change what's under the radical, just how many are out front. If I have 2 root 7s and I get 3 more, how many will I have altogether? You guessed it, or you knew it, 5 root 7. I have 7 fourth roots of 5 minus 2 cube roots of 5. The indices are not the same, therefore the radicals are not the same, therefore I can't combine these, and I just leave it. This is simplest radical form. Over here I have 4 square roots of xy, and I get 5 more. If I had 4 and I get 5, I now have 9 of those creatures. Alrighty. Moving on. Sometimes before you add and subtract, you need to simplify. So in this case, I first look at this problem and it looks like I can't do anything to it. But if I do it in simplest radical form, 6 square root of 9 square root of 2, I just broke 18 apart. If I break 8 apart, I have square root of 4 square root of 2 minus 3, and then 72 I break into, and this is one you might break into a couple of them. You might break it into 9 and then 8 and realize that 8 is actually square root of 4 square root of 2. Now, this is 6 times the square root of 9, which is 3, 2, plus 4, square root of 4 is 2, square root of 2, minus 3, square root of 9 is 3, square root of 4 is 2, square root of 2. 6 times 3, 18 root 2, plus 4 times 2 is 8, root 2, minus 3 times 3 is 9, times 2 is 18, root 2. 18 of these plus 8 of these minus 18 of these leaves me with 8 root 2. When you're adding and subtracting radicals, you are really just combining like terms. Okay? Now, here's your chance to show that you understand. Try this one. Pause the video and try it. All right, you're back. Could you do square root of 25 square root of 2 plus 3 square root of 16 square root of 2 minus 5 square root of 9 square root of 2, 5 root 2 plus 3 times 4 root 2 minus 5 times 3 root 2, 5 root 2 plus 12 root 2 minus 15 root 2. You combine your like terms and you should have 2 root 2. Everybody good? Fantastic. Okay, multiplying binomial radical expressions. Recall FOIL. It's the same process, and sometimes it can be easier if you just create a table. You have 3, and then you have 2 root 5. You have 2, and you have 4 root 5. 2 times 3 is 6. 2 times 2 root 5 is 4 root 5. Multiply outside, multiply inside. 3 times, if I've got 3 of these guys, then that means I have 12 root 5. Here I'm going to have 4 times 2 is 8. Square root of 5 times square root of 5 is 5. So I wind up with 40. Now I add everything inside and I get 6 plus 40 is 46 plus 12 plus 4 is 16 root 5. Now the next one down here that I have multiplying, I'm also showing you that if you wind up with a binomial squared, remember that you must FOIL it, first, outer, inner, last. Now you can either FOIL, you don't have to use the multiplication box. You can simply do square root of 2 times square root of 2 is 2. Square root of 2 times minus square root of 3 is negative root 6. Negative root 3 times root 2 minus root 6. Negative root 3 times negative root 3 is plus 3. And then you can just put it all together and you have 5 minus 2 root 6. The table is simply a way to put things together. It's a way to look at things. Okay? If you don't like it, don't use it. But if you like it and it helps you to keep things straight, great. Okay? Now, I don't know why I have this twice. So, we're just going to get rid of that one. Rationalizing binomial radical denominators. Now here, notice, if I just multiply by square root of 5 over square root of 5, I'm going to get 3 root 5 plus 5 over root 5 minus 5. That did not get rid of the radical in the denominator, and it really just made it more complex. Well, think difference of squares. The difference of squares, if I have a plus b and I multiply it times a minus b, I get a squared minus b squared. The individual a and the individual b drop out. A conjugate, it's the opposite of this guy. So instead of 1 minus root 5, I'm going to multiply the top by 1 plus root 5 and the denominator by 1 plus root 5. You make the second term negative, not both terms. Now, the numerator, yes, you have to FOIL it out. So 3 times 1 is 3, plus 3 root 5, plus root 5, plus 5. Firsts, outers, inners, last, over. And this one I'll multiply out to show you. 1 times 1 is 1. 1 times root 5 is root 5. Negative root 5 times 1 is minus root 5. Negative root 5 times positive root 5 is minus 5. Now I've got 3 plus 5 is 8. 3 root 5s and one more is plus 4 root 5s. And the denominator, the plus root 5 and the minus root 5 combine to make a 0 pair. 1 minus 5 is negative 4. And then I can reduce this. 8 divided by negative 4 is negative 2. 4 divided by negative 4 is 1. And I have my simplest radical form. It's a little longer, but it's not crazy. Okay, you know what to do. Simplify this using a conjugate. You back? Okay, first, what's the conjugate? Did you say 4 plus root 15? Yes, you got it. 4 plus root 15. The numerator's a little bit crazier and harder. 6 times 4 is 24. 6 times root 15 is plus 6 root 15. 4 times root 15. And then root 15 times root 15 is just 15. In the bottom, you're going to have the difference of squares. So the first term squared is 16. Then I'm going to subtract. Square root of 15 times square root of 15 is 15. Now, 24 plus 15 is 39. 6 plus 4 is 10. Square root of 15. 16 minus 15 is 1. So I don't have to put everything over 1. It needs to be simplified. Is that what you got? I hope so. If you're still confused about any part of this, please, and you weren't in class to ask questions, or you were in class and you're still confused after watching it a second time, please come and see me. Ask questions. Ask questions up front. That's the best thing that you can do. Okay, notice, multiplying radical expressions. We can put the things together or separate them underneath the radical. We use it to multiply radicals, simplify radical expressions, and multiply them. Dividing radicals, again, I can combine everything under the single radical or break it apart. You go forward or backwards, whichever makes more sense, whatever makes the problem easier to simplify. Now, to add or subtract, we must have like expressions. It is sometimes necessary to simplify each individual radical expression prior to adding or subtracting. When you're multiplying binomial radical expressions, use the same process that you used when you multiplied binomial expressions, namely FOIL. Do not forget, if you have square root of x plus y, quantity squared, you have to FOIL that. Don't just do x plus y squared. That'd be a big no-no, and you'll get the word FOIL written across your no-no. The conjugate can be used to rationalize the denominator when the denominator is a binomial radical expression. Okay? All good. Excellent.